Welcome, everyone, to today's podcast episode on the exciting quest for sustainable catalysts in green hydrogen production. We're diving deep into a fascinating paper from the Journal of the American Chemical Society, exploring a new approach to oxygen evolution reaction catalysts.
Green hydrogen is such a hot topic right now. Everyone's talking about it as a cleaner energy source, but it's not exactly easy to produce efficiently, is it?
That's right, Sally. One of the biggest bottlenecks is the oxygen evolution reaction, or OER, which is a crucial part of the process. Currently, the best catalysts rely on iridium, a rare and expensive metal. This new research tackles that problem head-on.
So, they're looking for alternatives, essentially. Something cheaper and more readily available?
Exactly. The researchers decided to focus on ruthenium, a far more abundant metal. It's significantly cheaper and even has higher intrinsic activity than iridium, but it has a major drawback: it's unstable under the acidic conditions needed for the OER.
So, the ruthenium dissolves during the process, rendering the catalyst useless?
Precisely. That's where their novel approach comes in. They used a machine learning framework, which is basically a powerful computer algorithm to screen thousands of possible catalyst compounds.
Wow, that's a lot of candidates to check. How did the machine learning part work?
They trained their model on over 36,000 mixed metal oxides. The model could predict the stability of these oxides under acidic conditions, a calculation that would usually require extensive, time-consuming tests. The algorithm efficiently predicted the stability of different compounds, enabling the researchers to narrow down the search.
And what was the result of this large-scale computational search?
They identified a winning candidate, a mixed oxide of ruthenium, chromium, and titanium, with the formula Ru0.6Cr0.2T0.2ox. The computer model showed this compound to be much more stable than pure ruthenium dioxide.
That's amazing. But how did they actually test this new material? Did it perform as well as predicted?
They did indeed synthesize and test this promising compound. The experimental results were outstanding. Their experiments confirmed the greatly improved stability of this material. The new catalyst ran at a high current density for over 200 hours and showed excellent activity.
So, they found a way to improve both activity and stability significantly?
Yes, absolutely. It's a huge improvement over what was previously possible with ruthenium. And that's where the chromium and titanium come in. Their computational work indicated that the titanium increased metal-oxygen covalency, which strengthened the bonds and improved stability. The chromium seemed to primarily enhance the catalyst's activity.
So, it's a synergistic effect, a kind of 1 + 1 = 3 situation where the combined elements are better than their individual parts?
Exactly. Their advanced characterization techniques like X-ray absorption spectroscopy revealed structural changes in the catalyst during operation, confirming the beneficial roles of chromium and titanium. The titanium helped to create a more rigid structure and reduce the dissolution of the ruthenium. The chromium played a key role in the improved activity.
This sounds like a real game changer for green hydrogen production. This could mean cheaper, more efficient, and sustainable ways to produce hydrogen fuel.
It definitely has huge implications for the future of clean energy. It's a great example of how combining computational approaches with cutting-edge experimental techniques can lead to transformative breakthroughs.
And the use of machine learning to screen such a vast chemical space, it's really groundbreaking. This approach could accelerate the development of many other important materials too.
Absolutely. This work truly showcases the power of combining advanced computational methods and careful experimental validation to tackle critical challenges in energy technology. We have learned how the demand for green hydrogen has highlighted the need for cost-effective catalysts, and how ruthenium, while promising, suffers from stability issues. The researchers ingeniously employed machine learning to explore a vast chemical space, identifying a superior mixed oxide catalyst containing ruthenium, chromium, and titanium. This catalyst showed improved stability and activity, paving the way for more efficient and sustainable green hydrogen production. Thanks for listening.